So hi guys, I know it's been a while, a couple months I think. Yeah, a lot of schoolwork, a lot of exams. Yeah, had to study and everything. Um, Remember when I said time management was a main goal for doing this podcast? That was not achieved. That was not achieved. So, here's a new idea. I actually stick to that idea. That's the new idea. That might not seem, you know, helpful, but believe me it will be. Believe me it will be. I just need to put it in my mind that, I'm on a time like I'm on limited time. That's it. For this podcast, yeah. So, anyways, I thought maybe we wouldn't do like as deep as a thing, as deep as a dive into anything. I thought maybe we'd do something quite nice, something, well, not light, obviously. It could cause death. Something light educationally. And so today we're doing tectonic plates and like plate tectonics. So, overall, there are two tectonic plates in the entire world. So, there's like two types. So, there's continental, which is older and less dense, and there's oceanic, which is younger and more dense. And so, because of convection currents in of the magma, so for example, hot magma rises because it's less dense, because all the particles are moving around, there's more spaces between the particles, and so it's less dense, and so it rises. But as it rises, it cools and it moves towards the side, and it sinks because it becomes more dense, because it condenses, the particles kind of condense together, and so it sinks. And so that's kind of like a convection current, and that's like a little cycle. It goes up, around, down, and back into that little cycle. Another explanation of the movement of these tectonic plates would be subduction zones. So, for example, in particular, because oceanic plates are more dense than continental plates, if they collide together, so if they converge together, the oceanic plates will, subduct underneath. So it will bend and kind of just move underneath the continental plate. And so as a result, a lot of scientists think that tectonic plates move because of this. And yeah. And so yeah, those are the two main reasons. There's a convection current of magma and there's a subduction zones of oceanic plates. And and there's more. There's three types of tectonic plate boundaries. So there's divergent. So, they move away from each other again because of convection or subduction zones. So, they move away from each other. So, for example, Iceland, like a place of diverging tectonic plates would be Iceland. So, you would see, so for example, in Iceland, I think you see a North Atlantic ridge where you can see the North American plate and the Eurasian plate. And I'm pretty sure there's a section along that ridge where you can touch both plates, which is pretty cool. And Iceland's like the only place on Earth that, you know, is the only land on Earth that is along a ridge. And I think that's pretty cool. And so, as a result, that's caused a lot of, volcanic activity, earthquake activity on Iceland. So, for example, was it last year? Yeah, last year there was a lot of volcanic eruptions and in Iceland, and that just caused a lot of disruptions. That's mainly because the plates are diverging from each other, moving away from each other. That's allowed like a um channel of magma to rise to the surface of the earth, and as a result, it could form like little shield volcanoes where the lava just kind of like cools down, and over time, it kind of builds and builds and builds into this big volcano. something like that. Yeah. Yeah, I would love to go to Iceland. It's pretty nice there. Um, Food, I don't know about the food. I would like to try it though. It's all like preserved food. I do like preserved food. Seems like a cool place, but you know what? It's expensive. Expensive. Anyways, let's move on. There's another type. There's actually two other types. But this other type is convergent, where they move towards each other, where they converge. So, there's two types of these. Two types of convergent plate boundaries. So, overall, there's three types of tectonic plate boundaries. There's divergent, convergent, and conservative. Divergent, i.e., Iceland. This is a little recap if you didn't know. Second type is convergent, which has two other subtypes, just to clear things up. So convergent, they move towards each other. There is destructive plate boundaries, which I've mentioned before, is more of a subduction zone, where the oceanic plate is more dense, and it moves under the continental plate, because, it's the continental plate is less dense than the oceanic plate. And so, as a result, that could cause a lot of earthquakes and volcanoes. Significantly, volcanoes do occur more at convergent and divergent, just to put that out there. So, yeah, destructive plate boundaries, subductive zone. And so, as the oceanic plate moves underneath the continental plate, it goes into the mantle, like the end of the oceanic plate goes into the mantle, gets heated up, turned into magma. Yeah. And that magma essentially becomes like the magma spewed by a volcano. So it melts and it goes up into this lava chamber. Well, no, not chamber, channel, up to the surface of the continental crust and could form a volcano. Additionally, a subductive zone could create like significant mountain ranges. So, let's see. For example, I think, the Andes mountain range in Chile. It's like the thin strip of land right next to Argentina. There's an Andes mountain range, and that's a result of the Nazca plate, Nazca, moving underneath the South American plate. Why? Because the Nazca plate is oceanic, and so more dense, it moves under. That has created volcanoes, but it has also created other landforms like the mountain range. So as the plate moves under the continental plate, it creates like the buildup of sediment on the oceanic plate, and so as a result, Andes mountain range was formed. I would like to like try hike that, but I don't know. Sounds a bit scary. Anyways, now this is the second subtype of the convergent plate boundaries. Collision. It's called collision. It's not called conservative, it's called collision. The second subtype of convergent plate boundaries is collision. So it's more of when the continental plates just collide. They hit each other. They just kind of move into each other. Yeah, they converge. Because they're, equal density. No two of the plates subduct or like go above the other. None of that happens. Instead, they kind of just bunch up together like accordions. Like I would make an accordion sound, but I can't. Accordion sounds. They would make like a accordion type of bunching up action. And so as a result, obviously it makes mountain ranges. So probably the most famous would be the Himalayas, where the Indian plate and the Eurasian plate just kind of converged. And so as a result, that just left, K2, Annapurna, Mount Everest in Nepal. That I'd say that would be the most famous. Now, this is the final type of tectonic plate boundaries. So, it's conservative slash transform. I was taught conservative, but apparently when I looked online for a little, checker up, because I haven't really revised this topic in ages, and I mean this has also kind of helped. I mean, I've also added a lot more information that I've learned through my research. But anyways, let's get back into it. Right. Um, Conservative or transform plate boundaries. I'd say conservative because, you would remember it more. DCC. You wouldn't remember DCT. I say DCC. Anyways, conservative. So it's where there's two plates and they just kind of move parallel from each other. So you got one plate. I'm gonna use my hands. You probably should too. Left hand up, right hand on the other side. Say your left hand is moving backwards. Right hand is moving backwards also at a slower rate. That's a conservative plate boundary. And so, I mean, again, the most famous would be San Andreas Fault, where, there's a lot of earthquakes. I mean, it's not as frequent as I've seen other places, but it's quite a lot of earthquakes. And so, building on earthquakes now. So, earthquakes can essentially occur everywhere. It can occur at any plate boundary, whereas volcanoes occur more at divergent plate boundaries and some convergent, mainly destructive plate boundaries. So convergent, conservative, you're more likely convergent as in like collision. Wait, no. Hold on. Yeah. Convergent and constructive, you're more likely to see earthquakes. And so that kind of works because the plates are moving against each other. And they're creating friction, and at some places they might get stuck. Or there might be so much surface, like, there might be so much friction that they won't move. And so as a result, that leads to the buildup of pressure, the buildup of tension. And as the plates move, because, again, drawing back to convection currents of magma and subduction zones, eventually it could like suddenly cause the release of tension. And so as a result, the plates would just jolt forwards, creating an earthquake. And so pretty big. And it's measured by magnitude. Yeah. Or is it the Richter scale? Yeah, Richter scale. Yeah. And it's got the seismographs. It's quite high tech. Yeah. Now, on to volcanoes. Volcanoes are crazy. They're quite crazy. So they produce like 100 to 300 billion tons of CO2, I think. But I mean, you might think, oh, that's pretty bad. That's quite a lot. Humans have it worse. We produce so much worse. We produce like 100 times more. So, pretty bad. Climate change, enhanced greenhouse effect. But there have been cases where I think, for example, Mount Pinatubo erupting in Indonesia in the 1990s I think Mount Pinatubo is a super volcano, and it's a pretty big volcano. When it erupted, it created such a dense cloud of ash. It just kind of reduced global temperatures. And so, a CO2 erupted, by a volcano doesn't always equate to global warming, just so you know. Volcanoes can also come from hotspots. So, when you're looking at a map that highlights the distribution of volcanoes across the world, and if you compare that to like a map or the outlines or the plate boundaries, you'll see that there's some volcanoes that occur like that aren't along those plate boundaries, and sometimes it's because of hotspots. Sometimes it's also because of faults. So first of all, hotspots first. So hotspots are like vulnerable areas in the Earth's crust or areas in the mantle where there's more magma. And so, for example, Hawaii. Hawaii's like a good like example of hotspots. Um, I will get back to Hawaii because it's also a good example of something else because of the hotspots. Volcanoes can also occur at faults. Earthquakes can also occur at faults. So again, if you compare a map of the plates, tectonic plates of the world, distribution of volcanoes and earthquakes, there are some that don't occur along those plate boundaries, and most of the time, well, not most of the time, some of the time it's because of these faults. So they're like little cracks, little areas of vulnerability along those plate boundaries. Well, yeah, from the plate boundaries where magma can seep up, or where friction in the plate boundary, friction can be caused. So I think a good example of a fault would be yeah, the active volcanoes in Arizona. Like, you wouldn't think there's volcanoes in Arizona, but there are plains of volcanoes in Arizona. There are like so many, they kind of just gave up giving them names. They gave them numbers, and they're all active. They're essentially mounds of lava, mounds of like volcanic ash standing up in these like flat lands, and it's pretty interesting. And sometimes you can see like the lava flow of the volcanoes. It's pretty cool, I think. It's so cool that, you know, there's like these fields of active volcanoes in America where you wouldn't think there would be volcanoes other than obviously Yellowstone and what's the other one? There's another one. They have another one. I keep forgetting what the other one is. But you wouldn't think that. But they have tons in Arizona. Mind blowing. I could not wrap my head around when I first saw it. Like, I've never been to Arizona. I just saw a video. Yeah, from the UK. Okay. Never been to Arizona at all. Um, yeah. And then again, I think like there's this type of volcano that really fascinates me. Like, it's always in the back of my mind. And they're calderas. So these are massive volcanoes. They used to have a little dome top, but because of like a super explosion thousands of years ago, millions of years ago probably, it's just kind of blown the top off. And so as a result, it's kind of left this crater of land. And I think that's so interesting. It's so interesting that something that we can't control is so powerful to just mass move a bunch of Earth. And I mean, that was kind of seen in what was it? The St. Helen eruption. St. Helen. Yeah, eruption of Mount St. Helens. Where one side of St. Helens was bulging because of the magma buildup and the pressure, and it led to like this landslide as it erupted, but at a larger, much larger scale. And I think that's so interesting. And you know what's more interesting than that? The one caldera that I first learned about calderas about was Campi Flegrei. I can't pronounce it. It's right next to what's it called? It's right next to Naples, where there's quite a lot of people living there. So many people living there. But these residents are right next to Mount Vesuvius, who's due in for another eruption, and Campi Flegrei, which is a supervolcano, a caldera, which essentially at this point is flat land because of a past explosion that was so powerful that it shot its top off. That's crazy. Ooh. But yeah, there's a lot of like monitoring things that are going on around Campi Flegrei and Mount Vesuvius to, give residents an accurate notice so they can evacuate pretty easily. But I think there was like a false alarm a couple decades ago where a neighborhood was kind of forced to evacuate, and they've never been back since. And so, I think, yeah, technology's improved since. So technology would be seismometers to see if there's, earthquakes beforehand. There's sulfur meters to, because before volcanoes usually erupt, they usually just kind of spew out a lot of sulfur. Yeah. Yeah. Calderas, crazy. And then movement on like tectonic plates. Back to tectonic plates. We're kind of moving around a lot here, but I'm just following my notes. Tectonic plates. They could cause like isostatic change. So that would be the rise or like decrease of ground level relevant to sea level. So, for example, it could cause land to pitch up or pitch down. So, yeah, as a result, it can cause sea level changes. And back to like Naples, back to Pompeii, that region. I think, yeah, the sea level's been retreating mainly because of an increase in in ground level, and so that's isostatic change. And there's been a lot of sea level changes because of isostatic change in that area. So, for example, there's this like ancient Roman architecture. I think it's an ancient Roman temple, but I'm not sure. Don't take my word for it. But there's markings on the temple, like pillars, that show like where the barnacles used to be. So, for example, when barnacles kind of just implant themselves on the rock, they secrete this acid that creates like a hole where they can burrow in. And so on these pillars, there are areas of there are darker lines which are like pretty densely populated barnacle populations, which you can tell by like the holes that are produced. And so that kind of shows that the sea levels changed dramatically like throughout civilization. And so, yeah, I mean, I'm jumping everywhere, but back to like methods you could like the different ways you could see if volcanic eruption is upcoming. Sea level change. Yeah. For example, you know, these are like case studies if you're studying like volcanoes in school. Um, you could use like what Naples with the sea level changes, the boats receding, sea level receding, and like the evidence of mussel populations on pretty high pillars, I would say. They're pretty high. Anyways, before I forget, I did say I would go back to Hawaii. Now, Hawaii is a really, really good example of a place to show that tectonic plates move. So hot spots do not move. They don't move. They're stuck in the mantle. They are stationary. But I mean, new ones do form. But plate tectonics, plates move. So in Hawaii, islands form from underwater volcanoes due to hotspot areas. And so over time, these islands emerge and they become submerged, the older they become. Whereas younger islands rise to the southeast. So, what does that show? So, for example, I'd say northwest, there are older islands. Southeast, there are younger islands. So, obviously, I think the scientists' thoughts weren't there new islands being formed in the northwest? That's where the old islands used to be. That's where, volcanic islands were formed. Why is there none there? Why are there new ones down in the southeast? And so that just kind of shows the movement of tectonic plates over a hotspot. So as a result of tectonic plates moving over the Hawaiian hotspot, it's just kind of created a chain of islands. And so as time passes, the newer islands will become older, they will become, more submerged by the ocean. And then there's newer islands, more towards the southeast, that are formed because of the plates moving over the hotspots. Yeah, and so that's why. And I mean, obviously, what we're talking about isn't very good. So, earthquakes, a lot of deaths, quite a lot of deaths. Volcanoes, obviously, quite a lot of deaths as well. Volcanoes, earthquakes can make areas uninhabitable. They can destroy infrastructure. So, for example, I think in 2010, correct me if I'm wrong, 2010 Haiti. Yeah, 2010 Haiti earthquake. It destroyed I think the prime minister's living quarters. It also destroyed the airport, and so less trade. Volcanoes, on the other hand, also a lot of destruction. So, for example, Montserrat has, I think, 4 volcanic areas. The main one that happened was between 1995 and 1997, which was Soufriere Hills. It's French. I don't know French. It's the Soufriere Hills. And because of the Soufriere Hills eruptions between 1995 and 1997, 2/3 of the island is you can't live there. It's excluded because of all the pyroclastic flow, all the lava flow, all the ash, and it practically buried the capital. So obviously what we're talking about is horrible. So let's go through what could be done to, reduce it a bit. So there's planning. Obviously you gotta educate the residents. The residents gotta know the risks, they gotta know what to do. So, for example, one way you would plan is, an evacuation route, a site where you would meet up, kind of like a fire drill. You give them aid backpacks, things like that. Another would be predicting. So, high tech. Obviously, that's going to be limited for quite a lot of countries. So, for example, Haiti, it's got a pretty low GDP, compared to, say, New Zealand. It's got a pretty high GDP. Um, and, I mean, there's a lot of differences in infrastructure. So, Japan's got shock absorbers. Haiti doesn't. Haiti doesn't. And so, yeah, it's caused a lot of problems. Um, what did I say? Prediction or protection? Prediction. Prediction, seismographs, um, yeah, seismographs, sulfur readings for volcanoes, but obviously that's limited by funds. Um, and then there's protection. So, can you provide aid? Any, do you have any schemes in place? Do you have any backup plans just in case something happens? Something like that. It's like the time. Well, hold on. Let me try to phrase this. When the hazard happens, like the time when the hazard happens. So, say a hazard happens at 4 a.m. Everyone's sleeping. The risks would be higher because everyone's sleeping. Say, for example, like in Christchurch, 2011, I think 2011 Christchurch. Yeah, 2011. 2011 Christchurch. Earthquake happened at noon, where everyone's out for lunch. The risks, like the death rate's gonna be lower as a result of that. And so, yeah, it's quite dependent on a lot of factors. So, yeah, hope you learned something. That's everything on plate tectonics. Yeah, I actually hope you learned something. I'll try to, I will be more timely. I will focus on time management the next academic year. That is what I will do, genuinely. I promise. I actually promise. Anyways, thanks y'all. See you guys next week.